Welcome to a fun, short little section where we introduce the damped harmonic oscillator. We're going to be talking about the damped harmonic oscillator for a ton of chapter 3 as well. It's going to be really important. It's going to be popping up all the time. And so we're going to start by saying, what is a damped harmonic oscillator? We've talked about simple or undamped harmonic oscillators in the context of springs with no friction, and they just bounce up and down and up and down. And you might say, Jason, how interesting is that actually? So we're going to be talking about damped, which is kind of like adding friction. Now, let me tell you something. The damped harmonic oscillator is more than just springs. And first off, springs are pretty interesting. There's a lot of things that we can do with springs, but we're going to be talking about things that are more than just springs here. So as some examples, we have some pictures. So the natural thing to talk about is springs, of course, for the damped harmonic oscillator. You can think of shocks in your car, right? Your shocks in your car, you go over a bump, this absorbs the bump. That does a couple things. That makes things more comfortable for you. And that also, if it keeps you on the road, right? If you weren't absorbing the bumps, and if there was a bump, your car would get launched off the road, which is really not what you want when you're driving. Ask me about all the times I've gone hydroplaning, okay? So that does help with that. And again, what we have is, inside of these shock absorbers, we have these springs, and they're in some sort of like oil, and that's going to be dampening or absorbing some of that friction. So again, we can model that mathematically with this damped harmonic oscillator. It's also used in RLC circuits. Again, I'm not an electrical engineer, but if you were an electrical engineer, you might see something like this. And that also uses damped harmonic oscillators. Also, glucose levels. Your glucose regulatory system actually functions as a damped harmonic oscillator, which is quite interesting as well. And essentially, right, what we have is this oscillation that's getting closer to zero, or some equilibrium, let's say, is really what we're looking at here. Again, we can see it in one way as a spring that is like bouncing, and then of course, because of friction and stuff, it's going to lose all that energy. It's going to reach that equilibrium. But of course, it can be seen in a lot of other ways as well. So that's kind of what we're starting with. And we're also going to go back to our undamped harmonic oscillator, which is md squared y. Let's try to be consistent on my notation. dt squared equals negative ky, right? Force is mass times acceleration, and then Hooke's law, force is equal to negative k times y. Y is the position. We could write that as a system of equations as well, and we're going to go back to writing it as a system too. But before we do that, let's take undamped to damped. So for undamped, right, we said there's no friction. These forces are just equal. Now for damped, what we're going to do is we're going to make it a little assumption. And again, this is a huge thing that I want you to always keep in your mind. Modeling is what differential equations is really all about, in my opinion. Again, somewhat of a biased opinion, but always think about modeling. In modeling, we start with assumptions, and then we say, how do we incorporate that into math? So we're going to assume, and again, this is a pretty good assumption, but it's not 100% accurate. Friction is actually a pretty complicated subject, a lot more than we might think. So we're going to assume that the strength of all damping, and that might include friction, it might include air resistance, it might include other factors as well. We're going to assume that strength is proportional to the velocity. The more movement in the system, the more damping is going to happen. The more movement, the more friction is another way you can think about this. All right, so that's what we're going to start. Well, how do we incorporate that? Remember what is proportional means, right? That means something's going to be equal to a constant times the thing. What was velocity? Velocity was dy dt. So really what we have here is we have some other constant, and we can just add it to one side of the equation. Negative ky minus b times dy dt equals m times d squared y dt squared. So again, if we think about the force of the spring is not just going to be proportional to the position, but it's also going to be subtracted by some constant times the velocity. And you might think, but Jason, doesn't friction work the opposite side as the force, right? Like you might think, well, if this is negative, shouldn't this be positive? Because they're kind of undoing each other. And the answer is yes, they are undoing each other, because think about a spring, right? If I have a spring, and again, maybe here's my equilibrium, and I have some kind of spring, right? We know the spring is going to be like the position is positive here, but we know the spring is going to be pulling it to the left. So in general, for pretty much every spring system that I can think of, outside of any like initial conditions, maybe not say y prime, right? But the force of these is going to be opposite, right? If y is positive, the spring's going to be pulling it in the negative direction. So a lot of times these are opposites. But anyway, take the physics knowledge with a grain of salt. I'm more of a mathematician, but that's one way of kind of thinking about it. So let's rewrite this, clean this up, and see what our model is going to be for undamped harmonic oscillators. So if we do that, let's get everything on the same side. That's very common. We don't like negatives. Let's add everything over. We're going to get m times d squared y dt squared plus b dy dt plus ky equals 0. And then we can divide everything by m again for these differential equations of second order. Again, it's very nice to have the highest term for our derivative to have a coefficient of 1. So it's very normal to divide everything by m. We'll get d squared y dt squared plus b over m times dy dt plus k over m times y equals 0. And then oftentimes we also just clean this up. We call this some parameter p and some parameter q, just to make things a little nicer to look at. But again, variables and parameters are in such a way that you can call them whatever the heck you want. So if you are writing it as a second order differential equation, this is what you're going to get. All right, and that's very common. Again, where p is b over m and q is k over y. We could also write this as a system if we wanted to, right? dy dt is just the velocity. And dv dt, what's dv dt going to be? It's this. Oops, that should have a second derivative. Well, subtract all that stuff over and you'll get it. dv dt is going to be negative p times dy dt, which is v, minus q times y. And here we have two expressions for our model for a damped harmonic oscillator. We'll be talking about more of what we can do with that, how we can guess some solutions and do some qualitative analysis as well using phase portraits in the next two videos.